start the lecture, remember on Tuesday we have a quiz about chapter 28 and chapter 29. Okay, so last time we introduced Faraday's law of induction, and we said the very interesting observation is that when a magnetic field changes, it induces an EMF. Okay, so if you have a loop and you have the magnetic field changing, it will induce an EMF and induce a current. And we said this induced EMF and induced current opposes the change in the magnetic field. And we expressed this mathematically, and we said the induced EMF is given by minus the derivative of the flux, the magnetic flux, with respect of time. Okay, and we said this minus is what we refer to as Lenz's law. So I want to give credit to Lenz's law. Okay, so Henrik Friedrich Lenz, he lived in the early 1800s. He's a Russian physicist. Okay, and he is noted for Lenz's law of electrodynamics. And the law says an induced current has a direction such that the magnetic field, due to the current, opposes the change in the magnetic flux that induces this current. So it opposes the change. It does not oppose the direction, it opposes the change of the magnetic field. So if I were to highlight this in red, it opposes the change. It doesn't like changing magnetic flux, so the induced EMF opposes this change. So let me go to presentation mode and see how it applies in the different situations we have seen earlier. We already did that for a couple of cases, I guess. Okay, so here, if we have the North Pole getting closer to the loop, we're pushing this permanent magnet into the loop, and I want to determine the direction of the induced current, in this loop. Do you think it's clockwise or counterclockwise? Think about it. Who says clockwise? Raise your hand. Counterclockwise? Alright, so let's see. Counterclockwise. So first of all, this is the magnetic field. Remember, the magnetic field goes out of the North Pole and towards the South Pole. So this is the direction of the magnetic field. And is it increasing or decreasing? The magnetic field is, the magnetic flux is increasing. So this is B increasing. Okay, so the induced magnetic field has to oppose that. So it's going to be in the opposite direction. It does not like the change because it's increasing flux, so it opposes it. So in order to determine the current, we have to point our thumb along the direction of the current and see if it opposes it, so it must be the current is counterclockwise in order for it to be into the page. So the current in this case is like this. Okay, so let's check if we're right. So yes, it is clockwise. So it looks like almost all of you were wrong. I said clockwise, nobody raised his or her hand. I said counterclockwise, everybody almost raised their hand. Let's check again. All right. So now the North Pole is being taken away. It's taken away. So do you think the induced current is clockwise or counterclockwise? Huh? Counterclockwise. It's the opposite of the other one. Huh? لأنه the flux. So here, okay. So here, the magnetic field is still in this direction, but it is, so the magnetic field is still in this direction, but it is decreasing. The flux, hence, is decreasing. So the induced EMF is opposing that. So since it's decreasing, the induced EMF is going to be something like this. It opposes the change. Okay? So in order to determine the current, we have to point the thumb in the direction of the current. So in order for it to be coming out of the page, the current has to be in the counterclockwise direction. So it opposes the change. The induced EMF opposes the change. Remember, to determine the direction of the magnetic field and the current, you point your thumb in the direction of the current and you swing with your 4 fingers. It will give you the direction of the magnetic field. Let's try another case. Okay, so this is correct here. All right, so the current is counterclockwise. And all right, let's take another one. So here we are bringing the South Pole close to the loop. What do you think? So, is it clockwise or counterclockwise? So let me ask. Clockwise. Who says it's clockwise? Okay. Counterclockwise. There are many undecided, looks like. Huh? Undecided? Okay. Make up your mind. All right. So let's see. So now, how is the magnetic field direction? We know it's going into the South Pole. The B field goes out of the north and into the south. And since this is you're bringing it closer, so this is increasing. It's increasing. So the induced magnetic field has to oppose that. It has to oppose the increase. So it's going to be in this direction, be induced. It opposes the change. This flux now is increasing, so it will oppose that. And so in order to determine the current, so I can point my thumb and I have to swing out of the page. So the current is going to be like this. All right. So this is going to be counterclockwise. So let's see. Yeah. So this is the increasing flux, magnetic field. This is the induced. It has to oppose the change in the magnetic flux, and so the current is counterclockwise. All right. All right. Good. All right. So how about this? Okay. So here we have this circuit, and we are closing the switch. We are closing the switch. Okay. So obviously, if you're closing the switch, you know the current is flowing out of the positive terminal of the battery. So the current is going to be like this current here. Okay. So we are closing the switch. Do you think the induced current is clockwise or counterclockwise? I'll give you some time to think about this. Okay, who says clockwise? Clockwise, raise your hand. Counterclockwise. Okay, we have a majority counterclockwise. Let's see if, all right, so we know this current is flowing like this. This current here, I, is flowing like this. Okay, so what is the magnetic field? So if you point your thumb along the direction of the current and you swing your 4 fingers, the magnetic field is inside. So this is the original magnetic field, and since you're closing the switch, it was open and you're closing it, so there is an increase. So this is increasing during the closing. The current is, you're establishing the current, so there is an increase. So the magnetic field has to, the induced magnetic field has to oppose this change. So it has to be in this direction, be induced. Okay, now in order for it to be in that direction, I have to point my thumb in the direction of the current and swing. It has to be outside, so the current is going to be like this, and it is counterclockwise. So correct. So this is again, this is the existing magnetic field and it's increasing. So this is the induced magnetic field, has to oppose a change, and so in this case it's a counterclockwise current. So now you're familiar with Lenz's law. All right, how about if you are opening the switch? So it should be the opposite thing. So you're closing the switch. Now this is magnetic field is going to be decreasing. So as the current, this current here is going to be going to zero, so it's decreasing current. So the magnetic field is decreasing, so the induced magnetic field is going to be in the opposing change. It's opposing the change, so it's going to be also inside the page. Okay, in order for it to be inside the page, we have to point our thumb. Okay, so it has to be clockwise. So Lenz's law is not difficult to apply. You have to determine what is happening to the existing magnetic field, which direction, and is it increasing or decreasing? Okay, and you have to find that the induced magnetic field is opposing the change. It's not opposing the direction of the B field, it's opposing the change. Remember, it's opposing the change, not opposing the direction. Here, for example, you can see that the induced magnetic field is in the same direction as the existing magnetic field. The reason is because this is decreasing, does not like the change, so it will oppose that. It will try to keep it. So this is Lenz's law. All right. Now, so you should be familiar with this. I already did this example. Okay. So next, and next. We did this. Next. Okay. So all of these we have done already. Okay, I'm going to, all right, let me go to the Kahoot and show. All right, this is going to be, and so let me start the Kahoot. So enter the Kahoot, please. 338-7898. Go ahead. Okay. So I'm going to skip the first few ones because we have already done them. Next. I don't know how to skip this. Skip. Next. 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 Skip. Next. Next. Somebody is entering me. All right. This one. Okay. So here we have a circular loop of wire following towards a wire carrying a current. So this is a wire carrying a current. This loop is following towards it. Okay. What is the direction of the induced current in the loop of the wire? The induced current here, is it clockwise, counterclockwise, zero, or impossible to determine? So I'll give you time to think about this. Ready? If you're ready, raise your hand. Raise your hand if you're ready. Okay, so I want everybody to make up your mind about this one. Okay, so let's start the Kahoot. Choose between A, B, C, or D. And you have 5 seconds remaining. All right, 16 are correct, but we still have 12 incorrect. All right. So, first of all, we have to determine what is the direction of the existing magnetic field. Okay, so the existing magnetic field, due to the current flowing here, so I point my thumb in the direction of the current and swing it with my 4 fingers. It's into the page. Now, so the magnetic field that is existing is into the page. So it is into the page. Now the question, is it increasing or decreasing? Increasing, because it's getting closer to the wire. And remember, for a wire, we said the magnetic field is mu0 I divided by 2 pi r. So if the distance is smaller, the magnetic field is going to be larger. Okay, so B is into the page and it is increasing. So B is increasing. So the induced magnetic field has to oppose the change. So it has to be outside. Let me draw it in red. Okay, so it has to be, B induced has to be outside. Okay, for it to be outside, I can determine the current. So if I point my thumb in this direction of the current and swing with my 4 fingers, it will be outside. So it is counterclockwise. So the induced current and induced EMF are in the counterclockwise direction. So the correct answer is B. Was it correct? Yeah, okay. All right. So we have we have many winners, I guess. All right. So let's do some problems. Okay. So here we have a coil or solenoid consists of 200 turns. 200 turns. Okay. Each turn is a square and of side 18 centimeters. A uniform magnetic field directed perpendicular to the plane of the coil is turned on. The figure shows the behavior of the magnetic magnitude of the magnetic field. So this is the magnetic field here. It increases linearly from 0 to 0.8 second, and then it decreases exponentially. So from t equal to 0 to 8 second, the field changes linearly from 0 to 0.5 Tesla. So B max here is 0.5 Tesla. After t 0.8 second, the magnitude of the field decays in time with an exponential decay. B is equal to B max exponential minus AT. Where A is the same constant, where A is some constant, and B max is 0.5 Tesla. What is the magnitude of the induced EMF in the coil between time equal to t equal to 0 and t equal to 0.8 second? Okay, so what do we use in this case? We use the equation. The induced EMF is minus the derivative of the flux with respect of time. All right, so now we have 200 turns. So in order we can determine the remember, for 200 turns we have to multiply the change of the flux in one, multiply it by n. So it's actually, so maybe I should write it. Okay, so this is going to be minus n. So this is for the total flux. So this is for a single loop dt. Okay, what is the flux through a single loop? We know the magnetic field is perpendicular to the surface, so the area vector and the magnetic field vector are in the same direction, so the angle between them. So remember, so this is going to be minus n, the derivative with respect of time of the flux, which is B dotted with dA. Okay, B dotted with dA. In this case, this is the magnetic field B is here. Okay, so this is minus N, and B, so A is going to be D squared, because this is a square. It's not a circular. So the area is D squared. Okay, times the derivative of the magnetic field. What's the derivative of the magnetic field? It's the slope. So I can write the induced EMF is minus N D squared. Okay, the derivative is a slope. So let me call this B2, B1. This is T1, T2. So the slope is going to be B2 minus B1 divided by T2 minus T1. So this is minus 200 times D squared, which is 0.18 squared. B2 is 0.5 Tesla minus 0 divided by the time, which is 0.8 seconds. Okay, so this is the flux. So the induced EMF, not it's negative. Now let's do it for this part. So it should be the same equation, except now we're going to take the derivative of the exponential. It's minus N D squared, the derivative of the exponential, derivative with respect of time, of B max exponential minus AT. Okay, so let's take the derivative of this. So the derivative of an exponential is known. So we have minus N D squared. The derivative of minus AT is minus A. So minus minus becomes A D squared. Okay, and we have B max exponential minus AT. Okay, so here they asked us to evaluate this at time equal to what is the magnitude of the induced EMF in the coil at t equal to 8 seconds. Okay, so what is the magnitude of the induced EMF in the coil after t equal to 0.8 seconds. So this is the equation. So we can replace all the values. We don't have the constant A here, so it stays as an equation. But very simple. We just applied this general equation. The induced EMF is minus the derivative of the magnetic flux. You have to remember, when you have n loops, you have a flux through one loop. You have to multiply it by n. So actually the induced EMF is n times the induced EMF in each of the loops of this solenoid. Okay, another problem. So here we have a solenoid inside a solenoid. Okay, so the current so this one is solenoid S. The current in the solenoid S is reduced at a steady state from 1.5 amps to 0 in 25 milliseconds. So let's draw it. This is a current in this solenoid. Okay, it decreases linearly from 1.5 amps to 0, and in the time t is equal 0.25 milliseconds, 0.25 10 to the minus 3 seconds. Okay, the question, what is the EMF induced in coil C? Coil C is this coil, the coil inside. So for coil C we have 130 turns. Okay, for the solenoid S we have 220 turns per centimeter. Okay, so what do we need to do? We still apply the equation. We know that the induced EMF is minus the derivative of the flux. So let me multiply it by n, and this is now NC, the n. So let me multiply it minus NC, the derivative of the flux through one coil with respect of time. Okay, so in order to determine the flux through one coil, I have to determine the magnetic field. So this is minus NC, the derivative of the area of one loop, times B. And since the area does not change, let me take it outside the integral, outside the derivative. dB dt. The area, so here, we need to determine B. What is the magnetic field due to a solenoid? We have an equation for that. The magnetic field due to a solenoid, okay? So first of all, if I grab my solenoid with my 4 fingers in the direction of the current, my thumb is pointing this direction. So the magnetic field is going to be in this direction. This is B, okay? And B is given by mu 0 Ni. Remember, number of turns per unit length, okay? So I can replace that here. Mu 0 and N are constant, they're not changing, but I is changing. So this becomes minus NC times the area of this small loop. So let me call it pi d over 2 squared. This is the area of this one here. The derivative of the flux becomes mu 0 times N. N is the number of coils, mu 0 small n. So let me call C, small n C, okay? Derivative of the current, di dt, okay? What is the derivative of the current? It's the slope, okay? And the slope, you can see here, it's a negative slope. Well, let me write it. So this is going to be minus nc pi d over 2 squared mu 0, number of turns for the big coil, S, this is S and S, coil S. Okay, the derivative of the current, let me call this I2. This is I2, which is 0, and this is I1, which is 1.5 T1 T2. So it's going to be I2, which is 0, minus 1.5 I1 divided by T2, which is 0.25 10 to the minus 3 minus 0. Okay, so this is the slope, and it's negative slope, so we obtain a result that is positive, and you can replace the numbers. We have everything in this equation. You just have to be careful with the unit, because here it says 20 turns per centimeter, so you have to convert it per meter, okay? So that's 220 times 100 turns per meter, and you find the final result. So if we look at the numbers, so this is the same steps that we have done. We have determined the slope here of the current, and we replaced it here, and we get an induced EMF of 75 millivolts. So here, it's like a principle of a transformer. You have one primary coil that you're passing a current through it. You have a secondary coil, and just happen to place the secondary coil inside the primary coil, okay? And the changing in the magnetic field in this primary coil will induce an EMF. So the EMF is induced in each of these loops, so you have to sum all of them, and you get a total EMF of 75 millivolts. Even though this loop is not connected to a battery, so you are inducing voltage and current in this loop without anything, just with induction, which is very powerful concept. Okay. Here is another example. So now we have a circuit. The circuit has a battery, okay, and a battery is connected to this loop. This loop is making a semicircle, and this semicircle happens to be in a magnetic field. This is a uniform magnetic field, but it is changing with time. So B is equal 4t squared plus 2t plus 3. B is in Tesla and t is in seconds. The radius is 0.2 meters. The resistance of this loop is 2 ohms. So we know it has a resistance of 2 ohms. What is the magnitude and the direction of the EMF induced around the loop at t equals to 10 seconds? All right, so I can write the equation. The induced EMF is always equal the minus derivative of the flux with respect of time. Okay, so here the flux minus the derivative with respect of time of B dotted with the A. Okay, and since B and A are in the same direction, and so B dotted the A is going to be minus the derivative with respect of time of the area is not changing. Remember, the area in this case is not changing. So let me take it outside the integral. So it's minus a, the derivative of b with respect of time. Except you have to be careful. The area here is half of a circle. It's not a full circle. So we can write the induced EMF is minus pi r squared divided by 2, because it's this area here, okay, times the derivative of the flux. So let's take the derivative of 4t squared, that's 8t plus 2, and that's it. Okay, so I have to determine this at t equal to 10 seconds, so it becomes minus pi, r is 0.2 meters squared divided by 2 times 8 times 10, that's 80, plus 2, that's 82, and this will give me the induced EMF. Okay? Now, let's try to determine the direction of the induced EMF. Okay? So, first of all, we are given the direction of the magnetic field. It's outside of the page. Now, the next question, is it increasing or decreasing? This magnetic field that exists, is it increasing or decreasing? Huh? You have an equation for it. Huh? It increases with time. It's increasing. It's all the factors, all the constants are positive. So if you increase time, it will increase. So this magnetic field outside of the page is increasing. That means the induced EMF has to oppose that. So the induced EMF has to be into the page. So let me use a red color. This is B induced. Now let me try to determine the direction of the current. Okay? So it has to be counterclockwise. If I point my thumb along this and swing with my 4 fingers, the current that is induced, or the induced EMF, so this is the induced current. It's opposed to the existing current. Notice the existing current is I, and the induced current is opposed to the existing current due to the battery. You see this battery here is causing this current. The induced EMF is now opposed to this current. Okay? So if we want to determine the current in the loop, I, it's going to be the induced EMF minus the EMF of the battery, the existing, divided by the resistance of this circuit. So this is going to be, I think if I'm not wrong, this is 5.15. Okay, so this is 5.15 minus the existing voltage, which is 2, divided by the resistance, which is 2 ohms. And so the total current, this is total current. This is equal. So it's equal to the I induced minus the existing I due to the battery. So you can see that you can have a circuit. You can have a circuit. You think it's operating perfectly, but there is a strong magnetic field, and this magnetic field is changing. It interferes with your circuit. It's inducing an EMF. It's inducing a current, and in this case, it's inducing a current and an EMF opposed to the existing battery. This is very interesting. So, if you have a circuit and it's close to a very strong magnetic field that is changing, it will interfere with your circuit. So you have to shield your circuit, otherwise you'll have problem. I was working with a company to remember this problem. We designed a quality assurance device for the water heater chambers. The water heater chambers, they are designed so that they have certain opening on some sides, and some other sides they have to be closed. And if there is a leakage, it can cause a fire. So they asked us to build a device to check where there is a leakage. Okay? So we designed a dome. Let me show you. It's okay, it's a side, but I think it's an interesting one, especially for those who might okay, so we put the chamber and we put it inside a dome, and we have a strobe light, very strong strobe light inside it, and we have photovoltaic cells all around. So this dome is a semi-spherical dome, and there is a platform, and according to the light pattern, so it's totally dark. When we turn on the light, we detect the light that is coming out of this chamber. Okay, so from the pattern of the light, we determine where there is leakage and where there is no leakage. Okay, and so we built this device for them, and we had a problem. Certain photovoltaic cells, they were always showing the light is on, there is light present. Okay, and it was giving wrong results. After we built the machine and they installed it in the American water heater factory, it was giving wrong results. Okay, so we had to investigate what is the problem. All right, so we went, and I was in charge of writing the software, the image recognition and so on. And we had an electrical engineer, he was in charge of the circuits and so on. So I said, I looked at the detectors that were all connected to this PCB board. And I said, it's strange, they are all connected to this PCB board. They are not, so there must be something wrong in the circuit of this PCB board. And what we found that the grounding, instead of having, usually when you have many boards, let's say you have one board here, one board here, one board here, you have always to bring the grounding to one single point. It's called a star pattern. Okay? We found that one of the boards was connected in such a way that it causes a loop in the ground. It causes a loop. So the magnetic field, due to this very strong current flowing through the strobe light, was inducing a current in this ground loop. And this board was always turning on. So this is induced magnetic, this is induced voltage, induced EMF in this PCB board due to the changing magnetic field. So what we did, we disconnected this PCB board and we soldered the wire to this point, this common point here, and it took care of the problem. Okay, so a real example where you can see a very strong magnetic field, changing magnetic field can interfere with your circuit. It can interfere with the functioning of your circuit. So you might have it for good reason. You might want to do that for certain instrument or design, but you don't want to do that. You want always to have your circuit operating correctly, so you want to avoid interference from magnetic fields. So here, this is the final result. Okay, do we have time for, okay, let's do this example. Okay, so here is another example. We have, in this case, we have a loop of width W and the height H, and the magnetic field in Tesla is given. It's varying as a function of time and varying as a function of position. So it's 4t squared x squared. B is normal to the loop, and it's given, it's into the page. What is the magnitude and direction of the induced EMF around the loop by the magnetic field at t equal to 1 second? All right. So here we have, so let me see. So first of all, the induced EMF is minus derivative of the flux with respect of t. So let me first of all determine the flux. All right. The flux is the integral of B dA. All right. Now I cannot simplify this B dotted with dA. I cannot simplify it. Why? Well, I can do some. B and the area vector are parallel to each other, so the dot product it becomes simple. So it becomes the integral of B dA. Okay, but B is changing; it's not constant. So what I'm going to do, I'm going to write a small element. So if I take this small element, the area, it's going to be, the flux is going to be B times this area element, which is going to be the height times this dx. So this is dx here. All right. Then I will replace it here. So this, the total flux becomes the integral of b h dx, and let me replace b. So b is 4 t squared h times x squared dx. All right, and we have to integrate this from x going from 0 to omega. So from 0 to omega. So what is this? The integral of x squared. So let's take 4t squared h. The integral of x squared is x cubed divided by 3. So this is the flux. Okay, we evaluated between 0 and omega, so this will be omega cubed. Correct? So we're evaluating it from x going to 0 to omega. Now I can replace this in this equation. So the flux here is minus the derivative, and it's with respect of time, of this flux, which is 4/3 h omega cubed t squared. Correct? So what's the derivative of t squared? It's 2t, so it's minus 8 divided by 3 h omega cubed and t. This is the induced EMF. Now I have to replace t at 0.1 second, so it becomes minus 8 divided by 3. H is 2 meters, omega is 3 meters cubed, and t is 0.1 seconds. And you find the induced EMF. So this is a little bit difficult. Why? Because p is not constant here. So I had to first of all evaluate this integral, what is the flux. Okay? Because p is changing with x. It's not constant. Okay, so we found the flux, then we put it in this equation, and we'll get the derivative with respect of time. So very interesting problem. I don't think you'll get something like that in the exam. Okay, so the result is you get okay, so E induced in this case is 14.4. Oh, sorry, I forgot to determine the direction. Now, this is magnetic field into the page, and it's increasing with time. It's increasing time. So it is increasing, so the induced magnetic field has to be opposed to that. So it's going to be out of the page. In order for it to be out of the page, the current has to be like this. So the current is going to be in the counterclockwise. So the current is going to be, so this is B induced is out of the page, and the current, this is the induced EMF, or the current, EMF induced is in the counterclockwise direction. Okay, so that's correct. So the E induced, notice, this is how we indicate the direction of EMF. We draw an arrow, not on the circle, because usually when we do that, it indicates the current. So this is induced current due to this induced EMF, and it's counterclockwise. Okay. All right, let's go to the next topic. And let me go to presentation mode. You're following me? I hope so. I know it's heavy stuff, but very interesting stuff. All right. Okay. So let's assume you have a bar, it's a conducting bar, okay, and it's moving at a constant speed with a velocity v. So suppose the magnetic field, and suppose the magnetic field is uniform, and we move a conductor in the field. Okay? Now, since this is a conductor, it has free charges, free electrons. So let's try to determine the direction of the magnetic force on these charges. Okay? So the magnetic field is into the page, and what do we have? We have an equation that says F is equal BLV, yeah? Is it? No, sorry. FB is V crossed with B. We had QVB, yes. So many equations. QVB. All right? Now, so let's do QVB. V, the charges are moving in this direction. So V is like this. B is into the page. V, B. The force is upward, but it's a negative charge, so it's opposed. So they will experience a force that is downward. The 3 electrons, they will experience a force downward when the bar is moving. Let's assume we are pulling it at a constant speed. These electrons, when they move to this side, they leave behind a positive side on the other, on the top. So the 3 electrons move here, they leave behind a positive bar on the top. So now we have accumulation of negative charges on one side and positive charges on one other side. What do we have? We have an electric field. So we have an electric field. The electric field is always pointing from positive to negative. So if we draw the electric field here, so we have the electric field is going to be like this. Correct? From positive to negative. Now, what is the electric force due to this electric field on the electrons? It's in the opposite direction because remember this is a negative charge and F is equal to QE. So this is FE is equal to QE. So there will be an electric force on the opposite direction. So these free electrons, they are subjected to force by the magnetic field in one direction, and when they go and accumulate in the other direction, they generate an electric field that forces them in the other direction. This push and pull will continue until the two forces are equal. When the two forces are equal, it will stay in equilibrium. This is what we call induced EMF because we are accumulating negative charges on this side. We are accumulating positive charges, or we're leaving behind positive charges on the other side. And we have an induced electric field, and this is an induced EMF. Remember, electric field, for a uniform electric field, E is equal to the VDX, or the delta V over delta X. So we are inducing an EMF. So a bar moving through this magnetic field experiences an induced EMF. Okay, and if we want to determine this induced EMF, so first of all, we said we reach equilibrium when the force, the electrostatic force, and the magnetic force are equal. So if you put QE is equal to QVB, you get E is equal to VB. And we know the electric field E is equal to the EMF divided by the distance, I guess L here. Okay, so let me use always absolute values here, so in order not to confuse. And I can determine E, so you can see E in this case is going to be the electric field times L, so it's the electric field times L. Electric field is equal to V, so it's VBL. V. So the induced EMF in this bar is going to be equal to the velocity of the bar times the magnitude of the magnetic field strength and the length of the bar. Okay? Interesting observation. All right? So now notice that we have an induced EMF even though we do not have a loop in this case. We don't have a loop, we don't have necessarily a flux changing. What we are seeing here is that we have an induced electric field. And it's this electric field that is giving us this voltage difference between the two ends, this end and the other end. Okay? So keep that in mind, we'll come back to that principle. Now let's make it more exciting. And let's now make it a circuit so that there is a loop and there is a bar here. And we are moving this bar with an applied force. Okay, so this is considered a circuit shown. The bar is pulled to the right with the velocity v under the influence of an applied force. Okay, so let's draw this circuit here. So this circuit has a resistance here. Okay, now we said this bar will have an induced EMF that is equal to BLV. Okay, and so the current that is induced, this current, so originally we did not have a battery. This is a circuit without a battery. But when we start moving this, what we did, we started changing the flux through the circuit. Okay, well, we induced an EMF here, and when we induce the EMF, we start having a current. Okay, and this current is going to be equal to BLV divided by R, because the resistance is R, so it's going to be the induced EMF BLV divided by R. So very strange. Even though we don't have a battery, by just moving a bar, moving a mechanical motion is now generating electricity. Moving a bar in a magnetic field, this magnetic field is not changing, by the way. What is changing is we're inducing the EMF in this bar, the electric field. So here electrons in the bar are moving, and so they experience a magnetic force. As a result, a potential difference is established, as we mentioned earlier. Okay, the flux, okay, in this case, so here, this is the equation of the flux, B dotted with dA. All right, now if we look at the flux through the circuit, this is L and this is X. The flux is the magnetic field B times the area, so it's Lx. Now take the derivative of that. Take the derivative of that to determine. So the induced EMF is minus the derivative of the flux with respect of time, the flux through the circuit. So it's minus the derivative of BLX. So this is the flux here. And when you take the B is not changing, L is not changing. What is changing is X, because the bar, when you're moving the bar, the X is increasing. Okay? So now it becomes dx dt, which is V. So this is another way of determining that the induced EMF is minus BLV. Minus BLV. And so we can determine the direction. So here is the flux that is existing, the magnetic field that is existing is into the page. It's increasing because you're moving the bar here, so the area is increasing. So it is increasing, so the induced magnetic field is going to be opposed to this change, so it's going to be outside. So it's going to be outside. If it's outside, then I can determine the direction of the current. If it's outside, so my thumb has to be pointing in this direction of the current. So this is the induced current. It should say induced, okay? So it is counterclockwise. If the bar was moved instead of this direction to that direction, what will happen? Is the current going to be in the same direction? It will be opposite direction. Because flux, the magnetic field is going to be decreasing, the flux is decreasing, sorry. The flux is decreasing through this as you move this way. So since the flux is decreasing, the induced EMF is going to oppose that change, so it will generate a magnetic field that is into the page. And hence the current will be in the opposite direction. Okay? Yes? This is an existing magnetic field. This is there. Okay, the induced one is going to oppose the change. What is the change now? Notice, we're not changing B now. We're changing the flux, because when you move this, the flux through this loop is increasing because the area is changing. Remember, we said to change the flux, you can either change B, you can change A, or you change the angle between them. Remember, we had a slide where we had an angle between B and the area vector A, and we said you can change the flux either by changing B, or changing the area, or changing the angle between them. Here, what we're changing, we're not changing B, we're changing the area. Since we're increasing the area, the flux is increasing. B times A. Okay? So that's why the induced, so the induced is going to be opposed to this change. The flux is going to be increasing, so the flux due to this existing magnetic field is increasing, so it's going to oppose it. It's going to generate a magnetic field in the other direction to counteract this change. It doesn't like change. Okay? So Lenz's law gives us the direction. Thank God. Okay, so this is, I just explained this. I said if you move in the opposite direction, you will induce a current in the opposite direction. This is given by Lenz's law. Okay? All right. So now, let's do some, we want to determine the work that you will do to pull a conducting loop out of a uniform magnetic field. Well, the work appears as thermal energy in the loop. So we will see that if you apply an external force, so this is a magnetic field here. This is a loop. The magnetic field is only on this part, and you're going to pull this loop out of this. When you pull this loop, okay, the amount of work you're going to do is going to convert into thermal heat into this resistance. So we assume this is like a resistance. It will show up as a resistance in the circuit. Remember, from physics 121, if you are pulling with a certain force F and a certain velocity V, we can get the power. So remember, so this is what we're going to do. We're going to prove that the power, this applied power, by pulling at a constant force and constant velocity, try to remember the power, remember the power, the work is Fx, and the power is a derivative of work with respect of time, or delta W. So this is going to be F dx dt. So it's going to be Fv. So this is we're just illustrating. The power that you'll be exerting is going to be equal to the power dissipated in this loop. This current is going to be the induced current. So changing the flux, so we are going to be inducing an EMF, an induced current. And this loop has a resistance, so it will appear as heat. Okay? So the rate at which work is done to pull the loop out of the uniform magnetic field is going to be equal to the rate at which thermal energy is dissipated in the loop, or the resistance of the loop. Okay? So this is what we will show. Let's do step by step. We know the induced EMF, it should be really absolute value here. Okay? The flux is the integral of B dotted with dA, and now, so the area, it's equal to B times A, and the area, now this is the area here. So it's equal to L, which is the height of the loop, times X, which is the width of the loop that is into the magnetic field, that is inside the magnetic field. So this is the area, Bx. All right? So E induced is the derivative of the flux, so we don't want to carry the signs. So since the flux is BLX, we know that the induced EMF is BLV. We have already shown this earlier. We have shown that the induced is minus BLV, so this is the, all right? Now, let us try to determine, so the flux is decreasing, and since the flux is decreasing, yes, so here, since we're pulling, the flux is decreasing, okay, the induced B must be into the page to oppose this change, because, so B is into the page, we're reducing the flux because the area is getting smaller. It does not like to see a decreasing flux, so it will oppose an induced magnetic field in the direction, the same direction as the existing one, because the existing one, the flux is decreasing, so it will generate. Okay, so since it's going to be into the page, so the current is going to be in the clockwise direction. All right, so the current and the induced EMF. So now I can draw this equivalent circuit. This is the induced EMF, it's clockwise. This is the induced current, I can put induced current, and it has a resistance R. Okay, I can determine the current I by dividing the induced EMF by the resistance of the circuit. It's the Ohm's law, V is equal Ri. So I can get the current. This is now an equation for the induced current. It's BLV divided by R. The induced EMF, the magnitude is BLV. Okay, so, and the current, induced current, is BLV divided by the resistance of this loop. So it's BLV over R. All right. So next, yes. I استعملت absolutely so that I don't keep to carrying the sign. لأنه induced EMF is minus BLV from previous derivation. It's minus BLV. So I just use absolute value, so I don't make mistakes. All right. So now let's look at the forces that are applied by this magnetic field on these elements. Okay. So remember, this is a current. The current is flowing in this direction. So it's flowing in this direction. And we said if a current is if a wire is conducting current and it's magnetic field, you will experience a force. And the force is given by ILB, IL crossed with B. So let's do ILB. So for this element, the L vector is like this. Okay, the B vector is like this. It's into the page, so the force is down. Force is down on this element. For that element, the current now is flowing backwards from left to right, here from right to left. So the force is going to be upward. So this force and this force, since this length and this length are the same, the currents are the same, these two forces will cancel each other. What do we have remaining? We have remaining this part. So let's do ILB. So the current is moving up. So the L vector is like this. The B vector is into the page. The L vector is up. The B vector into the page. The force is like this. So this is the force. This is the force that this loop will experience due to the current moving, or current is into magnetic field. So the fact that we are inducing a current here, this loop will be subjected to magnetic forces due to the existing magnetic field. Okay? So now, in order for us to move this loop at a constant velocity, the forces in the x direction has to be zero, the sum of the forces. You cannot move it at a constant direction, constant velocity. So that means F applied has to be equal to this force in order to be able to move the loop pull the loop at a constant velocity. Stay with me, Huda. Okay? So we have the sum of the forces is equal to 0. Okay, so F applied is going to be equal to F1. Okay, and F1 is ILB, IL crossed with B. Since the angle is 90 degrees, sine of 90 is 1. So F1 is equal ILB. So the applied force, in order to be able to move this loop at a constant velocity, has to be equal ILB. All right. So now I can determine the power. The power is F times V. F is ILB, okay, and times V. So we can obtain, and we know the current, we have previous equation, the induced current, we said it's BLV divided by R. What is it? So this current here is BLV divided by R, BLV divided by R, times LBV. So we obtain that the applied power due to the applied force is V squared, L squared, V squared divided by R. V squared? Yes. V squared, L squared, V squared divided by R. This is the applied power by pulling. Now, let's do the power dissipation through the loop. Okay, so this is the power due to this force pulling the loop at a constant velocity. Okay? Now let's try to determine the power through the loop. What do we have? We have the power, the electric power is, we can use VI. Yes. So the induced EMF times I, we know this is BLV, and I is BLV divided by R. So this is going to be also equal B squared, L squared, V squared divided by R. So it is equal to this. So the power dissipation through this loop, the resistance of this loop, the electric power is B squared L squared V squared divided by R, and the power we're exerting to pull the loop at the constant velocity is also equal to B squared L squared V squared over R. So we just have proven that the amount of power or the energy per unit time that you're exerting on this loop is appearing as heat in this loop. Okay, so this is what we just have done, and so we can say we have shown that the applied power is equal to the electric power, or F applied times V is equal to Ri squared. You can also write it that way. Okay, so work that you do to pull a conducting loop out of a uniform magnetic field appears as thermal energy in the loop. Okay, very interesting, huh? So here we're combining concepts from physics 121, Newton's law and power and so on, physics 122, induced currents and forces, and so it's really putting things together in a very nice way. All right, so here is a question, and let me go to the code. So and show discard. Go back to the same Kahoot if you left it. Okay, so 3387898, 3387998. Okay, and answer for me this question. On the figure, a given applied force of magnitude F results in a constant speed V. Okay, so this is the applied force, and a power input P. Imagine that the force is increased so that the constant speed of the bar is double, 2V. So we double the speed of the bar, 2V. Under these conditions, what are the new force and the new power input? What is this new force here, and what is the new power? Okay, so here you have 4 choices, and think about it. For those who have the slide, you can go back to the previous slide. Okay. Unfortunately, I cannot write on the Kahoot. I cannot write with my pen the equations. So if you have the slide presentation, you can. All right. So tell me, what do you think? So we said the force is equal ILB, and I is PLV over R. Okay? Yes? Naam? The code is 3387898. 3387898. يلا شباب يلا. Okay, so ready? Raise your hand if you're ready. Okay, so let's start. Five. Okay, nice. 20 are correct and 8 incorrect. That's very good. All right. So here, what did we have from the previous equation? We said F is equal IL times B, okay, and I is BLV over R. So this is BLV over R times B. So this is going to be B squared LV divided by R. So if we double V, we double the force. So this or this. Now let's look at the power. The power P applied is F times V. So it's going to be B squared L V squared divided by R here. Okay, so if we double V, we quadruple P. Yes. ما سمعتكش. So here, ILB, okay? And we said I is here. Oh, we forget L. Thank you. Yes, we forgot the L. So this is yes. So it's L squared V. Thank you, and L squared. Okay. So B squared, L squared, V squared. So the power is quadrupled, is 4 times that of the original one. So the correct answer in this case is what is it? C. Okay. All right. So here's the math. All right. Yes. Okay. Let me see if I can. This I cannot cover in 3 minutes. This one. Yes. All right. So here, a conducting bar illustrated in figure moves on 2 frictionless parallel rails in the presence of a uniform magnetic field directed into the page. The bar has a mass m and its length is L. The bar is given an initial velocity v initial to the right and is released at t equal to 0. Using Newton's law, find the speed of the bar as a function of time after it is released. Okay, so here we give it an initial speed v initial, okay, and so it has a mass m. Using Newton's law, find the speed of the bar as a function of time after it is released. So actually, yes, so let's, all right, so here the force, we said FB, the force that is equal to the mass times acceleration, and the force is ILB. This is the magnetic force on this element L here is ILB, okay, is equal m dv dt. Since we know the current is equal BLV divided by R, we have derived this before because this is the induced EMF, and induced EMF divided by R, we can replace it here and we can get mass times acceleration, which is m dv dt, is equal minus BLV divided by R, which is the current, times LB. So we obtain this is equal B squared L squared over R times V. Okay, so now we end up with an equation and we want to solve for V. So notice here we have dV dt and I have V here. What I can do, I can divide by V on this side and I can bring dt on this side. So I obtain dV over V is minus B squared L squared divided by MR times dt. Now if I integrate both sides, okay, I can get the integral of 1 over V dV is equal minus B squared L squared divided by MR times the integral with respect of time. This, the integral of 1 over V is log of V. So we get log of V over V initial is minus BL squared MR over T. This is very similar to equation we have seen before, the exponential decay. So this means V, if you take the exponential of both sides, you obtain that V is equal VI exponential minus T over tau, where tau is equal to this element. So next time we will